Hello guys, good morning. Good morning to all of you. How are you all? Today in this session, we'll be discussing the postulates of quantum mechanics, and it may take maybe a couple of lectures. So we have learned about the mathematical tools of quantum mechanics. Now these postulates of quantum mechanics is a little bit more advanced, you can say, where we will be using the mathematical tools, and this postulates of quantum mechanics is also like backbone of quantum mechanics. Okay, many things will be governed by these postulates. So that is why postulates of understanding postulates of quantum mechanics is really very essential. Quantum mechanics. So without any further ado, let's start. Postulates of quantum mechanics. So today's lecture, I am little busy today, so I will not make the lecture lengthy. Let's see how much we cover today. The postulate 1, there are 4 or 5 postulates of this quantum mechanics. The first postulate deals with the state of a system. So you see, the state of any physical system is specified at each time by a state vector psi of t. This is a ket psi t in a Hilbert space. Psi t contains and serves as the basis to extract all the necessary information about the system. So psi will contain all the information. You can find momentum, you can find energy, and you can find any other things from the wave function psi. Any superposition of state vectors is also a state vectors. So remember this one. So now what is the way to represent this psi of t? So let's say we have a system, the state of a system. How do they explain a system? We explain it by some coordinates, okay, or degrees of freedom. They say a state of a system having n degrees of freedom can be completely specified by a function, let's say psi, of coordinates q1, q2, q3. Let's say there are n number of coordinates, and another one that is time t. So this function is known as the wave function, which is called good morning Siva, Ranjani, Harry. Where is Murli today? Wave function, or it is also known as state function or state vector of the system. So this is important. Wave function or state function or state vector. So it is a function of q1, q2, q3, depending on the number of degrees of freedom along with time. And this wave function must follow certain properties. Properties of wave function, although we have shared it into the group, the properties of a wave function, you know what should we call as a wave function? The first property it should follow is that psi and its derivatives, psi and its derivatives must be continuous. Psi and its derivatives must be continuous. There should be no discontinuity. It should be finite. It's not like it is getting diverged. It must be finite. And the last one is single valued. Single valued. Single valued over the domain of the variable psi. Over the domain of the variable psi. So, what is the single valued? We have already talked about this single valued. Good morning, Murli. Single valued we have already talked about in mathematical physics. So, you see, if you have a function, let's say for the time I am representing it by this psi of x versus x. So, it can be something like this. Okay. Now, if you have some function in this way, it is like this. So, you can see at one value of x you are getting multiple values of psi x. So, this is multi-valued function. So, this kind of function is not eligible to be called as a wave function. This one is single valued. At each point of x we have only one value of psi x. So, it must be so continuous, finite and single valued over the domain of the variable of psi. So, this much is enough for the properties of, we should not number. In one line all the information is encoded. Now, you should remember or rather keep it as a note that all possible information can be extracted from this wave function. All possible information about the system can be derived from the wave function. Now, you see the representation of wave function. If you represent the wave function in terms of coordinate and time, then we will call it coordinate representation. Coordinate representation. Now, you can also represent this wave function in terms of momentum and time. So, when you represent it by as a function of momentum and time, this will be termed as, this will be in the momentum representation. Momentum representation, right? So, this is the first postulate. The first postulate deals with state of the system which is specified by a wave function, and these are some properties of wave function. Let us go to postulate number 2. Postulate number 2 deals with observables and operators. So, you have already studied about operators. So, to every physically measurable quantity A called an observable, physically measurable quantity called observable or dynamic variable. It may be, let us say, momentum. You, for the time being, you take the example with momentum. So, to every physically measurable quantity A called an observable or dynamic variable, there correspond a linear Hermitian operator. Linear Hermitian operator whose eigenvectors form a complete basis. Now, why Hermitian operator is chosen? Because the eigenvalue of the Hermitian operator is real. So, whenever you do the measurement, okay, what do you expect? If you are measuring something, you expect real values, you do not expect complex values. So, that is why Hermitian operator is taken, because Hermitian operator has real eigenvalues. And what is eigenvalue? Eigenvalue is like the measurement. Okay, so that is why Hermitian operator is chosen in quantum mechanics. So for an example, physically measurable quantity, let's say kinetic energy we are measuring. Kinetic energy. So kinetic energy is an observable for the time being. So we need a corresponding linear Hermitian operator A cap. So let's say if kinetic energy is A, then Hermitian operator will be A cap. So kinetic energy operator, we are denoting it by T. Okay, T cap, let's say. So what do you know about T? T is equals to P square by 2m. So Px square plus Py square plus Pz square divided by 2m. This is the this is the kinetic energy. Now you see P is equals to minus IH cut del, isn't it? Momentum operator P is equals to minus IH cut del. We have already talked about it. So if you go for Px, this will be minus IH cut del x. If you go for Pi, this will be minus IH cut del y. If you go for Pz, it will be minus IH cut del z. So each time it is square of it. So minus is absorbed, I square is minus 1. So minus h cut square on 2m and d square by dx square. So del square by del x square. For y, del square by del y square, z del square by del z square. Clear? Derivative also continuous means first order derivative should be 0. No. It is like, we'll deal with this. It is like we have a boundary. Okay. There are some region here, there are some region here. Let's say for the time being I am naming, this is x axis. Let's say this is from x1 to x2, and this is, let's say, x2 to x3. Okay. So x2 is the setting the boundary. So and at this boundary psi will be same, psi in this region at this boundary, and psi, we will calculate psi for different boundary, let's say. Okay, psi. So the value at x2 will be same. In a similar manner, you will have d psi by dx different in this region, d psi by dx different in this region, but at this boundary the value will be same. So it shows that it is continuous, not discontinuous. Now it is like you get some value in this region, you get some value here, in this region you get some other value. So it will show that this is discontinuous. So this kind of thing is not there. This and this value will be same. Okay, I hope this is understood, Murli. So this is equals to minus h cut square by 2m, and what is this operator? This is the Laplacian operator. Clear? All observable physical quantity must be Hermitian operator. Yes, because physical quantity means what? If you measure physical quantity, you will get real values. So if you want to get real eigenvalues, what operator you should choose? You should choose Hermitian operator. If it is anti-Hermitian, then the eigenvalues may be, you know, either purely imaginary or zero. These are the two possibilities, right? What are the eigenvalues of an Hermitian operator? They are real. And what are the eigenvalues of a skew Hermitian operator? That is purely imaginary or zero. So that is why every physical quantity will correspond to a Hermitian operator in quantum mechanics. Okay, let's move on. Do this problem. Consider a quantum mechanical system with three linear operators A, B, C, which are related by AB minus C is equals to I, where I is the identity operator. If A is equals to d dx, B equals to x, then C must be. So you can multiply psi on both sides and do the calculation. Whenever you see this kind of operator thing, d dx and all, you should operate with psi, otherwise you will get wrong results. AB minus C equals to I. So they are operators, so there should be hat over them. So it is like that. Now let's operate. So A is d dx, B is x minus C. C we do not know. Let's keep it like this. So let's operate it on psi. I times psi. So you see, it is nothing but d dx of x psi minus c psi is equals to I psi. What is the answer? Tell me, guys, quickly. Karthik, are you present? So this is psi plus x time d psi by dx minus c psi is equals to I psi, means psi. Actually, psi get cancelled, so you are left with x times c psi is equals to x time d dx psi. So obviously C corresponds to x times d dx. Acha, have I uploaded a studied lecture in the course folder? I am not sure about it. Whether have I uploaded the lecture in the course folder, a studied lecture? Harry, Murli. Is it done? Let's move on to the next question. If the operators A and B satisfy the commutation relation AB is equals to I, where I is the identity operator, then value of e to the power AB do this one. Yeah, I will upload both of the lectures, including today's lecture. AB, commutation of AB is equals to identity. Then what is the value of e to the power AB? You know, e to the power A is nothing but I. Look here, their operator. So we have to write, instead of writing 1, we have to write I plus A by 1 factorial plus A square by 2 factorial and so on. Morely, option A you are getting? Are you sure? Look, in quantum mechanics, answers are not so much straightforward. Okay, you have to think critically. I plus A by 1 factorial, A square by 2 factorial and so on, then B. So this corresponds to the commutation of IB plus commutation of AB, okay, plus 1 by 2 factorial commutation of A square B plus 1 by 3 factorial commutation of A cube B, and this will continue. So this first commutation is 0, commutation of AB is given to be I, and what about this half? Now what is this value? A square B, so you can write A into B, so it is nothing but A times commutation of AB plus AB commutation of ABA plus 1 by 3 factorial. We can write A cube is A square into, or A into A square, A into A square. So A into A square commutation of B plus A B A square. Okay, we can write it in this way. So what it gives you? It gives you I plus, look, AB is identity, AB is identity, A plus A is 2A, 2A by 2 is A, plus, here you see A square B, we have got 2A, right? Look, I am writing it here. It is given commutation of AB is equals to I, commutation of A square B, as you can see we have found out it is 2A, okay. Now commutation of A cube B, commutation of A cube B is A into A square B, so this is 3A square actually. A square B is 2A, so A into 2A, so 2A square plus A square equals to 3A square. So A to the power 4B will come, 4A cube, it will come out like that. So you can see it is some number, then A to the power that number minus 1, isn't it? So this term will come as A square by 2 factorial, isn't it? This 3 is getting cancelled, so it becomes 2 factorial. Then it will come A cube by 3 factorial and so on. So this is nothing but the e to the power a. So it is matching with option A. I hope this is clear. Now let's move on to this problem. The translational operator TL is defined as TL if it operates on f of x produces f of x minus L, where f of x is an arbitrary function of position and L is an constant. If the position operator is represented by x cap, then what is the value of TL x? You can use this formula: e to the power I px a by h cut f of x equals to f of x plus a, and functional operator of a b is equals to f prime of a commutation of ab. So can you do this? Look, we know that e to the power I px a by h cut while operating on f of x produces f of x plus a. Okay, and here what is given? It is given that TL, which is an operator, when it is applying on f of x, produces f of x minus L. So what we can write from here? If you compare these two expressions, what we can conclude about TL? So it is like if I write minus a here, then this will become f of x minus a. So here if it is x minus L, so if I write a is equals to minus L, then this will be equivalent to 12. So e to the power minus I L px by h cut, for obvious reasons. So what you have to find out? You have to find out the commutator of TL and x. Commutator of TL and x. So let's evaluate that. Commutator of TL and x. So this is e to the power minus I L px by h cut x. Now this formula will come up, f of a. So you can see this is a function of some variable with along with the commutator of b. So this is a prime of a commutator of ab. Okay. So here a is like px, an operator. Okay. So you can also give an operator symbol here as well. So derivative of this with respect to px. What is the derivative? Minus I L by h cut e to the power minus I L px by h cut times commutator of AB. A is Px here, x is x. So this is equals to minus IL by h cut e to the power minus IL Px by h cut. Commutator of Px, x is minus I h cut, because x Px is h cut, so Pxx is minus I h cut. And minus minus plus I into I square, that is minus again. H cut is getting cancelled, so minus L. And what is this e to the power minus IL Px by h cut? That is nothing but TL. So L times TL, because e to the power minus IL Px by h cut is the operator TL. So this is matching with option B. Harry, very good. Okay, let's go for postulates 3. What is the postulate 3? Measurements and eigenvalues of operators. Already we have, while discussing mathematical tools, we have already given you these hints before. Now it will be very easy for you to understand. The measurement of an observable A. Observable means any measurable physical quantity you can imagine, maybe kinetic energy, momentum and all those stuff. The measurement of an observable A may be represented formally by the action of some operator A on a state vector psi t. Now psi contain all the information, you just need to apply different operator. If you apply momentum operator, you will get momentum. If you apply energy operator on this wave function, you will get energy. If you apply kinetic energy operator on this wave function, you will get kinetic energy, right? So the measurement of an observable A may be represented formally by the action of operator A on a state vector psi t. The only possible result of such a measurement is on of the eigenvalues. That's what I told. Okay, on of the eigenvalues an, which are real of the operator A, because this operator must be an Hermitian operator, and as a result of that you will get real eigenvalues. If the result of a measurement of A on state psi t is an, means the eigenvalues are an, the state of the system immediately after the measurement changes to psi n. So this happens in quantum mechanics. You have a system, the system has some state. Once you measure it, the state will be changed. It will not stay in the same state. After the measurement, it will be found in a new state. So previously it was in psi t state. Now immediately after taking the measurement, the state will change to psi n. So A you have applied on psi t and it made the psi t to psi n, and whatever value you get here, this is the measurement. An, you can, using the orthonormality condition, you can easily find an, isn't it? So an is equals to, you have to multiply with bra psi n. Okay, if you multiply with bra psi n, actually, if you multiply with bra psi n, then this will give you an. An is the component of psi t when projected onto the eigenvector psi n. We have also talked about it while discussing the significance of dot product. We have talked about it in the mathematical tools section. So this is the postulates 3. Now what is postulate 4? Postulate 4 deals with probabilistic outcome of measurements. Okay, at any point if you don't understand anything, you can let me know. This is probabilistic outcome of measurements. You know, in quantum mechanics, things are probabilistic. There is nothing like definite thing. And why the probabilistic thing is coming? Because of the uncertainty relation. Here we cannot precisely measure the position of the particle. We cannot precisely measure the momentum of the particle. We can measure with some error. So we can just say that there is some probability to find a particle here, because in quantum mechanics we represent it by wave function. So you imagine it in this way. You have a particle, let's say particle. For classical particle, you see it is definite at some location it is situated, but when you have a wave, we cannot talk about it, okay, where the particle should lie. If you consider the de Broglie hypothesis, it has some particle aspect as well as some wave aspect. So for the wave aspect, you cannot exactly say that the wave is situated here, because it is spatially extended, okay, it is extended over a large region. So what happened, let's say the particle is propagating, the corresponding wave is also propagating in the form of a wave packet actually. So actually this is the actual thing, wave packet. So wherever in the neighborhood of the particle, this amplitude will be maximum, okay, and this will be very much negligible. The amplitude will be very much negligible outside of it, but those are not zero. So what we say the probability to find the particle here is more as compared to finding the probability of finding the particle here. So it is probabilistic. Now there may be discrete spectra and continuous spectra. Discrete means eigenvalues are separated, discrete, and continuous you understand. So when measuring an observable A of a system in the state psi, obviously if the state change, this state vector will change, and as a result of that the measurement will change. So when measuring an observable A on a system in a state psi, the probability of obtaining one of the non-degenerate eigenvalues An, non-degenerate means single eigenvalue corresponding to single eigenvector, okay. So the probability of obtaining one of the non-degenerate eigenvalues of the corresponding operator A is given by this. This formula is quite important. Probability of obtaining An is given by, so psi n psi mod square divided by psi psi. Psi psi is the original state, okay. It is composed of let's say, if I give an example, psi, it is like A0 psi 0, A1 psi 1, A2 psi 2, and so on. Let's say instead of starting with A0, let's start with A1. A1 psi 1, A2 psi 2, and An, let's say psi n. So these A1, A2, A3 are eigenvalues. So what is the probability of getting N? So that is given by, you have to take the dot product of the corresponding state psi n with this psi mod square divided by psi psi, because the probability of getting this eigenvalue is the square of this mod an square. How do you get mod an square? By taking the dot product. By taking the dot product and mod square, you will get an square divided by psi psi. If it is normalized, if psi is normalized, you can see this denominator will be 1 and you will end up getting the coefficient square, okay. So if I am saying that psi is normalized and it has, let's say, 2 psi 1 plus 3 psi 2 minus 4 psi 3, okay. So if I am calling that we have a wave function like psi, this psi 1 corresponds to the ground state, psi 2 corresponding to the first excited state, psi 3 corresponding to the second excited state. So if I ask you what is the probability, if it is, let's say, normalized, 2 square 3 square, okay, we have to make it in this way so that it becomes normalized, but for the time being, let's constant we multiply, because we do not know, we have to calculate, okay. let's say psi is normalized, then what is the probability to find the particle in state psi3? So obviously what you're going to do, mod a3 square, this will be the probability. Now in here it may be, let's say, minus 1 by root 2 is there. So what is the probability? It will be 1 by 2 in this way. So why it is changing the state? So you can understand it in this way. Whenever we want to measure something, how will you measure system? Maybe with a laser light or something. So you are perturbing the system in the process of taking measurement. Measurement will not be taken without affecting the system, right? So once you start measuring, so you are sending some probe, right? So you are disturbing the system. So when you are disturbing the system state will be changed. That is why whenever you take measurement, you get it in some new state. Psi n is the eigenstate of A with energy eigenvalue n. If eigenvalue is n is m degenerate, means m fold degenerate, corresponding to the same eigenvalue if there are different eigenvectors. If it is m fold degenerate, then the corresponding formula will be this. Okay, j equals to 1 to m psi n j psi mod square divided by psi psi. Because as I told you, this is m fold degenerate, means the kth will be corresponding to, let's say, psi n 1, then psi n 2, psi n 3, and so on up to psi n n. So you have to take sum of them and take a square, and then you have to do. Okay. The act of measurement changes the state of the system from psi to psi n. If the system is already an eigenstate psi n of A, measurement of A will with certainty the corresponding eigenvalue A n. So A psi n is equals to A n psi n. Change in state, because we are in the process of measurement, we are perturbing the system. We are giving external influence to the system. So which is responsible for the change? So in quantum mechanics, people joke in this way that if you look at the system will be changed. So some person explain it in this way that if you are looking or observing a system, you are sending some light to the system, right? And that is changing the measurement. It is on the quantum level, so that is why you can imagine it in this way. In classical world, that is not appreciable. The same thing goes for continuous spectra. Mainly this discrete spectra is important, because in quantum mechanics we mainly see this discrete spectra. For continuous spectra, this relation, above relation, is valid for the relation 1, which is valid for discrete spectra. It can be extended to determine the probability density. For the discrete spectra, we can definitely find out the probability. Okay, here we find probability density in some range. Probability density that a measurement of A yields a value between A and A plus D on the system, which is initially in a state psi. So derivative dpa by dA is equals to this. So this is not so much used. The first one is mainly used. So let's say the probability density for finding the particle between x and x plus dx is given by dpx by dx is equals to mod psi x square divided by psi psi. Now in this regard, there is something called expectation value. Although we have already defined this expectation value, here you see expectation value of A with respect to psi is given by this psi A psi by psi psi. I have told you, right? So psi A psi by psi psi, it can be written in this way also, an psi mod square by psi psi. So expectation value can also be written as eigenvalue multiplied by the probability of obtaining that eigenvalues. Okay. The energy of a system is given by this psi h psi by psi psi. If psi is normalized, psi psi will be 1. So what is expectation value? Expectation value represents the average result of measuring A on the state psi, right? So one question came based on this expectation value. So this formula, this is general formula, psi si by psi psi, this is what you can apply. Other than that, a shortcut formula is this, An Pn. If you are given some state psi, then you find the eigenvalues. Eigenvalues how to find? That will be given, and this probability of getting that eigenvalue. Let's take a problem, then it will be more clear. This came in 2011 June. The wave function of a particle is given by this 1 by root 2 phi 0 plus I phi 1, where phi 0 and phi 1 are the normalized eigenfunctions with energies E0 and E1 corresponding to the ground state and first excited state respectively. The expectation value of the Hamiltonian in the state psi. So what is given? It is given psi. So we can represent in the bracket notation, ket psi is equals to 1 upon root 2 phi 0 plus I times phi 1. So we may require bra psi, so let's calculate bra psi as well. This is 1 by root 2 bra phi 0 minus I bra phi 1. No issue. Phi 0 and phi 1 are the normalized eigenfunctions with energies E0 and E1. What is this eigenvalue correspond to? If we apply Hamiltonian operator on the wave function, we get energy, eigenvalues, right? So what is further given? Psi 0, phi 0 and phi 1 are the normalized eigenfunctions with energies E0 and E1. So if I apply H Hamiltonian operator on phi 0, as per the question, it should give you E0. And if you apply, let's say phi 1, it should give you E1. So the expectation value of the Hamiltonian in the state psi. What is the expectation value of Hamiltonian? Expectation value of Hamiltonian in the state psi. You know the formula, psi h psi divided by psi psi. So this is the expectation value of the Hamiltonian. So let's put, this is bra psi. Bra psi is this 1 by root 2 phi 0 minus I phi 1 h ket psi 1 by root 2 phi 0 plus I phi 1 divided by psi psi. So if you take the scalar product of psi with psi, so 1 by root 2 phi 0 minus I phi 1 1 by root 2 phi 0 plus I phi 1. So this will remain as it is. Now you see what will be this h applying on phi 0, that is E0, and 1 by root 2 is there, so this will be E0 by root 2 times phi 0 plus h applying on phi 1 produces E1, and this I was there, so I E1 phi 1, and this one you see phi 0 phi 0, so 1 by root 2 square and minus I square. Look, we are using the orthonormality condition. Phi m, phi n is equals to delta mn. So if they are equal, then that will be 1. If they are not equal, then that will be 0. That is why phi 0 will produce 1. So 1 by root 2 into E0 by root 2. So it is E0 by 2. Look, phi 0 and phi 1 will be 0 because m not equals to 1. Only phi 1 and phi 1. So minus I into plus I E1. So I square is minus plus E1 divided by this is 1 by 2 plus 1. So 2 get cancelled. E0 plus 2 E1 and half plus 1 is 3 by 2. So 2 get cancelled. So it is 3. That is matching with option D. Is it clear or not? Harry, Murli, is it okay? Let's solve this problem, then we'll wrap up the session. Actually, I'm going home, so there will be a couple of days off. Monday, Tuesday will remain off. Hopefully, we'll start on Wednesday, or if possible, in the evening of Tuesday, otherwise Wednesday. Is it not a normalized wave function? Fourth state explain. First, second, this one. You see, you are taking the product. So phi 0, phi 0. Phi 0, phi 0 is 1. So 1 by root 2 into E0 by root 2, that is E0 by 2. Let's say phi 0 and phi 1. So phi 0, phi 1 will be 0. So that term is not counting. Only you see when these coefficients are equal, then it will be non-zero. Otherwise it will be 0. Phi 1 and phi 1. So minus I into plus I E1. So E1. Okay. And this is 1 by 2 plus 1. And this one we got, look, H applying on phi 0 is equals to E0, phi 0, H applying on phi 1, E1, phi 1. So psi is not 1, so that is not normalized. That is good question, Murli. Psi is not given to be normalized. Phi 0, phi 1 are normalized, but psi is not normalized. Can you do this? Consider the quantum state psi is equals to psi 1 plus 2 psi 2 plus 3 psi 3, where psi 1, psi 2, psi 3 are normalized eigenstate of a Hermitian operator H with eigenvalues 5, 2, 4. What is the expectation value of H? Similar manner. Tell me quickly. So kit psi is given. What about bra psi? Bra psi will be bra psi 1 plus 2 bra psi 2 plus 3 bra psi 3. Okay. Hermitian operator H with eigenvalues 5. It means H while operating on psi 1 producing eigenvalue 5. So 5 psi 1. H while operating on psi 2 produces eigenvalue 2. H while operating on psi 3 producing eigenvalue 4. So expectation value of H. Okay, let us calculate what is this value psi. So psi1 it is 1, 2 into 2, because they are normalized, it means psi m psi n, orthonormality condition will be satisfied. So 1 plus 2 plus 9. 1 plus 2 into 2, 4. 1 plus 4 plus 9, na? 5 plus 9, 14. This is psi h psi by psi psi. What answer are you getting, guys? So this is 1 upon 14 h psi. So you see 5 psi 1. Okay, brass psi 1 plus 2 psi 2, 3 psi 3. Brass psi, let's keep it as it is. H applying on psi. So H we are applying on this. So H psi 1 is 5 times psi 1. Okay, H psi 2 is 2 times, so 2 into 2, 4. 4 psi 2 plus 3 psi 3 is 3 into 4, 12 psi 3. So as you can see, 1 by 14 into 5 plus 2 into 4, 8 plus 3 into 12, 36. 36 plus 5, 41 plus 8, 49. 49 by 14, 3.5. Option D you are getting. Actually, I don't have pages to move on, so maybe I am blocking this. Is it clear? 3.5. Harry, Murli, is it clear? So this was all for today. We'll continue after this from the next day. I hope you find this session useful and you have found everything understandable. Bye bye, take care, enjoy a great weekend, and we may meet on 23rd or maybe 22nd evening. Bye bye, take care, guys.